Hello everyone, let's proceed to the discussion of the chapter work, energy and power. If you have any doubts, you can ask in the chat section. So the first question says that the sign of work done by a force on a body is important to understand. State carefully if the following quantities are positive or negative. So we know by definition of work that work is defined in physics as the dot product of force and displacement, and we can write it in the, if we write it in the magnitude form, then it would be equal to force times displacement cos theta, where theta is the angle between these two vectors. Now simply saying that if the movement is in the direction of force, then the work done will be positive, and if the movement is in the opposite direction of the applied force, then the work done will be negative. Now the first question is work done by a man in lifting a bucket out of a well by means of rope tied to the bucket. So here man is pulling the bucket, it means man is applying force in the upward direction, and bucket is moving in the upward direction as well, so the work done is positive in this case. Now the second question says that work done by gravitational force in the above case. Now since gravitational force is acting downwards and the bucket is moving upwards, so the work done by gravitational force in the same case is going to be negative. Now the third question says that work done by friction on body sliding down an inclined plane. So friction always opposes the motion, so work done is going to be negative in this case. And the fourth option is work done by an applied force on a body moving on the rough horizontal plane with uniform velocity. So the body moves with uniform velocity, indicating that the applied force is balanced by the friction. The applied friction is in the direction of displacement, so the work done by this force would be positive. Now work done by resistive force in air on vibrating pendulum in bringing it to rest. The resistive force of air acts opposite to the direction of motion of the pendulum. As the pendulum loses energy, eventually it will come to rest, and work done by the air resistance would be negative. I'll pause for a while. If you have doubt, and you can ask. Let's proceed to the next question. The next question says that body of mass 2 kg initially at rest moves under action of an applied horizontal force of 7 Newton on a table with the coefficient of kinetic friction of 0.1. Compute the work done. So here let us picturize this question at first. So a body of mass 2 kg moves initially at rest, moves under the action of an applied horizontal force of 7 Newton. So 7 Newton is applied in this direction, and the coefficient of friction mu would be equal to 0.1. Compute the work done by the applied force. Now we have to find out work done by this force, and we have to find out work done by friction, and we have to find out work done by net force on the body, and in the fourth option we have to find change in the kinetic energy of the body in 10 seconds. So we know that if in order to find the work done by the applied force, by any kind of force, we should know the force and the displacement in that direction. So here this is the applied force, that is 7 Newton is the applied force, and the opposing force is only the frictional force which is applied, which can be given by normal reaction multiplied by 0.1. Now normal reaction would be 20 Newton, so 20 Newton multiplied by 0.1 is the maximum frictional force would be there. And we have been given that the force is applied for 10 seconds, so we can find out what would be the displacement of this body in 10 seconds. When we know the acceleration of the body upon balancing the force, that is this is the 7 Newton, and in the opposite direction there would be equal to 2 Newton. So we can find out the net acceleration of this body, and thus we can find out all the work done. And change in kinetic energy would be equal to work done by all the forces. Thank you. Let's move to the next question. If you have doubts, you can ask. So let's move to the next question, that is 5.3. This question says that given the figure 5.11 are example of some potential energies function in one dimension. The total energy of the particle is indicated by the cross on the ordinate axis, that is in the y-axis. In each case, specify the reason, if any, in which the particle cannot be found in the given energy. Also indicate the minimum total energy of the particle must have in each case. Think of the simple physical context in which these potential energy shapes are relevant. So in this question, 4 figures are given and we have to find out in which reason the particle cannot be found. So let us first go to the basics about energy. We know that total energy is composed of kinetic energy plus potential energy, and total energy can't exceed any of these two energies. So this is the principle for solving this question. Now let us go to the first option. We haven't given that this is the total energy, so we can just draw a straight line. We see that after the particle crossed this x equal to a position, it has gone beyond the total energy of the given total energy. So we can say that the particle cannot stay, or a particle cannot be found in this domain, that is x greater than a. In second question, we have, again we will draw a straight line. So in this reason, we see that the particle has never came below the total energy level, that is it is always above the total energy level. So the particle cannot be found in any of its x domain, so we can say that it is not possible. Now in this figure, we see that particle is the total energy of the particle, the energy of the particle is within the boundary of the total energy between the domain x equals to minus infinity to minus b by 2, and then x equals to minus a by 2 to a by 2, and then x equals to b by 2 to beyond. So we can say that these are the plausible reasons where we can find the particle, and these are the reasons where we cannot find the particle. Now the last option is we will again draw a line of total energy. So now we can filter out what are the reasons, what are the plausible reasons in which particle can be found and can't be found. So again, when the particle's total energy is going beyond the specified level, we can say that the particle cannot be found in that zone. So we can see that at less than x equals to a, particle cannot be found, and at x equals to and at x greater than b, particle cannot be found. Let's move to the next question. So this says that the potential energy function for a particle executing simple linear harmonic motion is given by Vx equals to kx square by 2, where k is the force constant of the oscillator. For k equals to 0.5 Newton per meter, the graph of Vx versus x is shown in figure 5.12. Show that the particle of total energy 1 joule moving under this potential must turn back when it reaches x equals to plus minus 2. So we know that again total energy is equals to kinetic energy plus potential energy. Now we have to show that the total energy is given, that is 1 joule. It will always be equal to kinetic energy of the particle at any moment plus potential energy of the particle. Now we have to show that for k equals to 0.5, the graph of Vx versus x is shown in figure. Now we have to show that the particle must turn back when it reaches x equals to plus minus 2 meter. Now let us consider the limiting case, that is x equals to plus minus 2 meter. Now the potential energy of the particle at x equals to 2 meter would be k x square by 2. Now that would be equal to k times 4 by 2 or 2k. Now 2k is equals to 2 times 0.5, and that would be equal to 1 joule. Now if particle goes beyond 2 meter, then potential energy will rise above the total energy level. That's why it is not possible, and it must turn back so that the total energy remains constant and the law of conservation of energy remains valid. Let's move to the next question. If you have any doubts, you can ask. I will pause for a minute. Let's move to the next question. So here we have to answer the following questions. There are 4 questions. So the first question is, the casing of a rocket in flight burns up due to friction. At whose expense is the heat energy required for burning obtained, the rocket or the atmosphere? As the rocket, so we know that as rocket moves through the atmosphere, friction between the rocket's surface and air molecules generates heat. This friction force acts against the rocket's motion and converts kinetic energy into thermal energy. So the source of energy comes from the rocket. It is not coming from the atmosphere. Now the second question is, comets move around the sun in highly elliptical orbits. The gravitational force on the comet due to the sun is not normal to the comet's velocity in general. Yet the work done by gravitational force over every complete orbit in the comet is 0. Why? So we know that gravitational force is conservative in nature. That's why work done under the conservative force is not a path function. It is a point function. That is, it depends upon the point. Once it completes the circle, its work done is going to be 0. That's how the work done by gravitational force over every complete orbit of the comet is 0, because gravitational force is a conservative force in nature. Now the third question is, an artificial satellite orbiting the earth in very thin atmosphere loses its energy gradually due to dissipation against earth atmospheric resistance, however small. Why then does its speed increase progressively as it comes closer and closer to earth? So the question is saying that, let us assume that this was the level of satellite, and satellite has reached over here, and this is earth. So as it reaches down, its velocity increases. Why? Even though due to atmospheric burns, it loses some of its energy. So this happens because the satellite is losing potential energy and it is being converted into kinetic energy. That is why its speed is increasing as it coming to earth. Now the fourth question is, in figure 5.13, the man walks 2 meter carrying a mass of 15 kg in his hands. In figure 5.132, he walks the same distance pulling the rope behind him. The rope goes over the pulley and the mass of 15 kg hangs on its other end. In which case is the work done greater? So there are 2 cases. First, the man is lifting 15 kg weight and moving in this direction, and the second is man is pulling this thread that is tied to 15 kg over a pulley and it is pulling it. So in which case the work done is greater? So here work done is greater in case 2, because man is pulling via tension in the wire, and tension in the wire is in the upward direction, and the movement of this weight is also in the upward direction. So tension is working, doing work over here, and this work is going to be positive, and the agent that is applying tension is the man. That's how man is working. The work done by this man in the second case is greater than that of in the first case. If you have any doubts, you can ask. Let's move to the next question. The question says that underline the correct alternatives. When a conservative force does positive work on a body, the potential energy of the body increases or decreases or remains unaltered. So when a conservative force does positive work on the body, the potential energy of a body increases or decreases or remains unaltered. So let us understand a case over. Let us see a case over here. A ball is above the ground with level of height h. This is the ground level. Now the ball is over here, h1, and h is greater than h1. At h1 the potential energy is lower, and at h potential energy is higher, because we know that potential energy is given by mgh. Now the question said that when a conservative force does positive work, that is when the ball is brought from this height h to h1, the work done by conservative force, that is the gravitational force, should be positive. Now the initial case is this and the final case is this. The potential energy of the body increases or decreases or remains unaltered. So we can easily see that mgh is going to be higher than mgh1. So potential energy has decreased. So this would be the correct answer. Now the second question is, work done by a body against friction always results in the loss of kinetic or potential energy. So friction always acts when the body has a kinetic energy. That's why the correct alternative would be kinetic energy. The rate of change of total momentum of many particle system is proportional to the external force sum of the internal forces of the system. So according to Newton's second law, the rate of change of total momentum of the system is equal to the net external force acting on the system. Internal force cancel out due to Newton's third law. That's why it would be external force. Now the fourth option is, in the inelastic collision of two bodies, the quantities which do not change after collision are the total kinetic energy, total linear momentum, total energy of the system, or two. So in the inelastic collision, kinetic energy is not conserved, but total linear momentum and total energy are conserved. So it would be total linear momentum and total energy of the system are conserved. Let's move to the next question. So it says that state if the following statements are true or false. Give reason for your answer. In an elastic collision of two bodies, the momentum and energy of the body is conserved. In an elastic collision, total momentum and total kinetic energy of the system is conserved. However, the momentum and kinetic energy of each individual bodies are not necessarily conserved. That is, total momentum and energy of the system is conserved, not the individual body. Total energy of the system is always conserved, no matter what internal and external forces of the body are present. This is again false. The total energy of the system includes all forms of energy, that is the kinetic energy, potential energy, and thermal energy. According to the law of conservation of energy, total energy in a closed system is conserved. However, if external forces act on the system, they can do work on the system, converting energy from one form to another. So it can't be said that total energy of the system is conserved, always conserved. It is only conserved when there is no external force acting on the body. Now the third question is, work done in the motion of a body over a closed loop is zero for every force in nature. This is only true for conservative force in nature. So this is again false. Now the fourth option is, in an inelastic collision, the final kinetic energy is always less than that initial kinetic energy of the system. So it is generally true because energy dissipation happens, but it is not always true. In most inelastic collisions, the final kinetic energy is indeed less, but initial kinetic energy decreases because some kinetic energy is transformed into one form to another, such as heat or sound. So exception is, there is a special case where the final kinetic energy might be equal to or even greater than that of the initial kinetic energy. This can happen if external work is done on the system during the collision, if there is an explosion involved in the process. For example, explosive collisions. In some cases, objects may be initially at rest or moving slowly and then explode and releasing stored chemical energy. in the form of potential energy, which converts into kinetic energy. So these are the cases in which kinetic energy may be higher. Let's move to the next question. The question says that answer the following with reasons. In an elastic collision of the two billiard balls, is the total kinetic energy conserved during the short term of collision? So during the short term of collision, total kinetic energy is not conserved. In an elastic collision, while the total kinetic energy of the system is conserved before and after the collision, but during the actual contact between the balls, some of the kinetic energy is temporarily converted into potential energy due to the deformation of the ball. That's why it is not conserved during the collision. So the second question is the total linear momentum conserved during the short time of elastic collision of the two balls? So linear momentum is conserved during the short, yes, this is true. Linear momentum is conserved in any collision, elastic or inelastic, as long as no external forces are acting on the system. So this is true. In the third question we have, what are the answers to A and B for the inelastic collision? So for kinetic energy, the kinetic energy is not conserved during the short term of collision in the inelastic collision, like in the elastic collision as well. And the linear momentum, yes, again the total linear momentum is conserved in the short time of collision in an inelastic collision. As with the elastic collision, linear momentum is conserved in the inelastic collision due to internal forces being equal and opposite and the lack of external forces on the system. So linear momentum will only change if the external force is acting on the system. And the fourth question is, if the potential energy of the two billiard balls depends only on the separation distance between their centers, is the collision elastic or inelastic? So the collision would be elastic in nature. If the potential energy between the two billiard balls depend only on the separation distance between their centers, it implies that the force during the collision are conservative, and in an elastic collision the total mechanical energy is conserved. Since the potential energy depends only on the separation distance, any potential gain during the collision will be fully converted back into kinetic energy as the ball will separate. So no kinetic energy loss will happen to non-conservative forces like friction, deformation or heat, indicating that the collision is elastic. Let's move to the next question. A body is initially at rest. It undergoes one-dimensional motion with the constant acceleration. The power delivered to it at time t is proportional to. So power, we know that power is the derivative of work done. With respect to time. So let us first find out the expression for work done. Work done, we know that work done is equals to force times the displacement. So work done is F dot S, where S is given by half ATA square, since its initial velocity is 0. Now we can multiply with this with mass times acceleration. So it would be equal to, so the expression for work would be equal to KT square. Now if we differentiate it with respect to t, then we will get the power, which will be proportional to t to the power of 1. So the second alternative will be correct. Next question is, the body is moving unidirectionally under the influence of source of constant power. Its displacement in time t is proportional to. So here power is constant. So let us represent this energy by kinetic energy, that is half MVA square. Now derivative of it would be equal to constant, because the power is constant, and derivative of energy with respect to time is going to be constant. So this is the derivative, and we have equated it to equal to k. Now if we integrate this on both the direction, we will see that displacement v dot dt will represent the displacement, and this is proportional to t raised to the power 3 by 2. Let's move to the next question. If you have any doubt, you can ask right now. I will take a break for 1 minute. The question says that a body constrained with to move along the z-axis of the coordinate axis is subjected to a constant force F given by F equals to -1 minus I cap plus 2j cap plus 3k cap. What where I, j and k are the unit vectors along the xyz axis of the system? What is the work done by this force in this moving a distance of 4 meter along z axis? So body can move only in the z axis, and we know the formula for force for the work done, that is F dot d. We can easily find out the vector product, dot vector product, because the displacement would be equal to 4k cap and the force is given, so dot product would be 12 joule. Let's move to the next question. It says that an electron and proton are ejected in a cosmic ray experiment, the first with the kinetic energy of 10 electron volt and the second with the 100 electron volt. Which is faster, the electron or the proton? So here the kinetic energy of these two, electron and proton, are given. Now we know the expression for kinetic energy, that is half mv square. Now we have to tell that which is faster, that is either the velocity of, either the speed of electron is faster or that of the proton is faster. So since we have been given the value of kinetic energy, so we can find out the ratio between them, and the only unknown would be equal to velocity of these two quantities, which we have to find out the relative one. So we see here that the velocity of electron is 13.5 times that of the protons. That is, since electron is lighter, its velocity is much higher than that of the proton, even though the proton is having higher energy than that of the electron, higher kinetic energy. Let's move to the next question. This question says that raindrop of 2 millimeter falls down from a height of 500 meter above the ground. It falls with decreasing acceleration due to viscous resistance of the air until it's half of its original height. It attains its maximum terminal speed and moves with uniform speed thereafter. What is the work done by the gravitational force on the raindrop in the first and the second half of its journey? What is the work done by resistive force in the entire journey if its speed on reaching the ground is 10 meter per second? So the raindrop started from stationary state and it reaches to the ground at 10 meter per second. So we can apply work energy theorem over here. We know the force acting on the raindrop would be gravitational force first and the frictional force second. So the gravitational force the work done by gravitational force can be easily found out by change in potential energy. And since we know the difference in the kinetic energy, so the work energy theorem always says that the work done by all the forces, whether it is conservative or non-conservative, is equal to change in kinetic energy. That's how we can find out the work done by friction force. Total work done will include work done by gravitational force and work done by friction force. We can find out work done by gravitational force with the formula mgh. Since it is a point function, as gravitational force is conservative in nature, it can be easily found out by mgh, and the only unknown would be frictional force, work done by frictional force, which can be found out by work energy theorem. Let's move to the next question. So the question says that a molecule in gas container hits horizontal wall with a speed of 200 meter per second and angle 30 second and an angle 30 degree with the normal, and rebounds with the same speed. Is the momentum conserved in the collision? So we see here that there is no any other forces acting on the system, and when there is no any other forces acting on the system, momentum is always conserved. So we can easily say that this momentum is conserved over here. A pump on the ground floor of the building can pump water up to fill the tank of the volume of 30 meter cube in 15 minutes. If the tank is 40 meter off the ground, what is the efficiency? And the efficiency of the pump is 30%. How much electrical power is consumed by the pump? So here we have been given the efficiency of the pump, that is 30%, and we have been given the the volume of water that has to be lifted by 40 meter. So here we have to find out how much electric power is consumed by the pump. So we know that power is the rate of delivery of work, that is work done per unit time. Work done per unit time. So here we have to find out work done, and we have been given the time, that is 15 minutes. So in 15 minutes we have to lift 30 meter cube of water to 40 meter height. Since we have to work against gravitational force, so we can easily found out the work done in this case by change of potential energy, that is mgh. Height would be equal to 40 meter, and mg, where mass can be found out by multiplying the volume with density, and g is the gravitational constant, so acceleration to gravity, sorry. So the work done required would be found out by mgh. And since the pump has got 30% of efficiency, so in order to deliver this much of power, 70% more power is required in order to deliver this much of power, as the pump has got only 30% of the efficiency. So we can use this equation, that is 30% of total power that is to be consumed is equals to 13.066 kilowatt. So x should be equal to, that is the required power would be equal to 43.55 kilowatt. So here two identical balls bearing in a contact with each other and resting on the frictionless table are hit head on by another ball bearing on the same mass moving initially with the speed of v. If the collision is elastic, which of the following is possible result after collision? So here the case is, this ball 2 and 3 is resting initially, and ball 1 came with velocity v and it hit these two balls. Then what would be the case? Either those two balls will move with the velocity of v by 2, or the second case where ball 3 will only move with the speed of v, and the third case is only all these three balls with the move with the speed of v by 3. So since it is given that collision is elastic, that is kinetic energy final is equals to going to be kinetic energy initial. We know that kinetic energy initial is half mv square. Now we will equate the final kinetic energy in all these three cases and will compare it with the initial kinetic energy. The case in which initial kinetic energy equals the final kinetic energy, that case would be going to be equal to that case is going to be plausible case in this case, in this scenario. So second option, we see that the final kinetic energy is half mv square. So this is going to be the correct option. Let's move to the next question. A bob of pendulum A is released from 30 degree from the vertical. Ball hits another bob of B of same mass resting on the table as shown in the figure 5.5. How high does the ball A rise of the collision? Neglect the size of the balls and assume the collision to be elastic. So in the elastic collision, we know that initial kinetic energy is equals to final kinetic energy, and initial momentum is equals to final momentum. So from this case, we can find out the final velocity of v1 and v2, and we see that v1 will be at rest, and the mass that was initially at rest will continue to move on with the speed imparted by ball A. These two formulas should be remembered in this case. So this question is again talking about efficiency, that is when the ball is falling to a height of 1.5 meter, then what would be the final kinetic energy when the ball is at position B? So it is given that 5% of the energy gets dissipated, so only 95% of the energy will remain. So we can easily multiply with this the potential energy, 0.95 times the potential energy of the body, initial potential energy, that would be equal to the final energy. Now since this potential energy will be converted into kinetic energy, we can equate it to half mv square, and then we can find out the velocity, terminal velocity. Let's move to the next question. If you have any doubts, you can ask in the comment section. irrespective of whichever question I'm in. So the question says that a trolley of mass 300 kg carrying a sandbag of 25 kg is moving uniformly with the speed of 27 km per hour on a frictionless track. After a while, the sand starts leaking out of a hole on the floor of the trolley at the rate of 0.05 kg per second. What is the speed of the trolley after the entire sandbag is empty? So here again, the system is not being affected as there is no any external force acting on the system. So the assuming trolley and sand to be the system under consideration, no net force is acting on the system, so the truck won't change its speed. Also, if the sand is falling, then it would continue with the same speed. A body of mass 0.5 kg travels in a straight line with the velocity given by expression a x to the power 3 by 2, where a is equals to 5 per meter per second square. What is the work done by net force during its displacement from x0 to x equals to 2 meter? So we will use the integral formula for work done over here. We have been given the velocity. We can easily find out acceleration by finding that dv by dt. This will give us acceleration, and we have to find out work done. So we will integrate v with dx. This will give us we will integrate with vt, and then this will give us the displacement, or we don't need displacement from this. So we can easily we will get the mass time, we will get acceleration from this, and mass is given, so mass times acceleration will be the force, and since the displacement is from 0 to x, we can integrate it to 0 to x using this formula, that is f dot dx, and since this is a definite integral, so we will get the value, that is 50 joule. Moving to the next question. So here the blade of a windmill sweeps out a circle of area A. If the wind flows at a velocity v perpendicular to the circle, what is the mass of the air passing through in time t? So we have to find out mass passing through time t. So area is given. Now mass can be found out by multiplying volume with density, that is rho. Volume can be found out by multiplying area with speed of the wind. So this will give us the volumetric rate flowing through the windmill, and when we multiply it with density, then we will get the mass flow rate dm by dt through the windmill. Now what is the kinetic energy of the air? We will get the mass. So, and we have also been given the velocity of the wind, that is 36 km per hour. So we can easily calculate the kinetic energy by mv square, half mv square. Now the third question is, assuming that the windmill converts 25% of the wind's energy into electrical energy. So here wind energy is being referred to the kinetic energy that we found out by half mv square. Now if we multiply it with 0.25, then we will get the electrical energy that is being converted. So yeah, so that is being asked, so we can easily calculate using this expression. If you have any doubts, you can ask. Moving to the next question. So a person trying to lose weight diet lifts 10 kg mass 1000 times to a height of 0.5 meter each time. Assume that the potential energy lost each time she lowers the mass is dissipated, how much work she has to do against gravitational force? So here she is raising the potential energy of the 10 kg mass each time she is lifting the weight. So each time she is lifting the weight, she is doing mgh kind of work, where h is 0.5 meter and m is 10 kg and g we all know we can use 9.8 meter per second square. So this much amount of work is done by her in each cycle, and she does 1000 cycles. So we can simply multiply it with 1000, and then we will get a value, potential energy dissipated in 1000 lifts, that is 49,000 joule. Now the second question is, fat supplies 3.8 into 10 to the power 7 joule of energy per kilogram. which is converted to mechanical energy with 20% of efficiency rate. How much fat will she use up? Now, per kg of the fat gives this much amount of joule. Now, energy converted into mechanical energy is this. So, if she burns 1 kg of fat, only 20% of it is converted into mechanical energy, and that is 7.6 into 10 to the power 6 joule. Now, if so, this much amount of energy is being used up by 1 kg of the fat. So, if she burns 1 kg of the fat, she is able to work for this much of. She is able to do this much of work. Now, if we divide this much of work with the required work done, then we can find out how much kg she will burn up. So, if after dividing, we get 6.45 into 10 to the power minus 3 kg of fat she burns in the whole 1000 cycle. Moving to the next question. We see that a family uses 10 kilowatt of power. Direct solar energy is incident on the horizontal surface at an average rate of 200 watts per square meter. If 20% of energy is converted into useful electrical energy, how large an area is needed to supply 8 kilowatt? Compare this area to that of the roof of the typical house. So output efficiency here is 20%. Now 20% of the incident light, that is 200 watts, to 200 watt is incident, and its 20% is being converted into usable form of energy. So after 200 watts, that is incident, only 40 watt is being converted into the usable energy. So area required would be equal to total required watts divided by 40 watts, because this is the unit square work. This is the unit square power that we are receiving from the sun. So after this, we will get the value of 200 meters square that would be required. So considering the the square plot, we will require 14.14 times 14.14 meter square plot for this kind of energy to be harnessed. If you have any doubts, you can ask. I will pause for a few minutes.